In manufacturing, some parts are born for mass production. They belong to molds, to injection molding. But sometimes a part is taken off that track, made only for a handful of pieces.
Hi everyone, this is Lingo from WayKen. Take a look at this part in my hand. How do you think it was made? That's right, it's an automotive lighting component, the outer lens of a center-high mounted stop lamp. It's transparent, lightweight, and covered with fine optical textures. When light passes through, these tiny structures act like a precisely sculpted surface. In mass production, parts like this are almost always injection molded. But this project was different. The customer only needed 40 pieces. Building a mold would easily cost over $10,000. So they came to WayKen hoping to make it with CNC machining instead. And that raises a question. Can a part designed for injection molding really be made with CNC while still meeting optical and visual requirements? The answer is yes, but it's far from simple, and the challenge starts with the material. The customer specified plexiglass 8N, a PMMA material. But here's the issue. It's an optical grade material designed for injection molding, and it comes in pellets. CNC machining, however, requires solid sheets. So what do? We will melt the raw material and extrude it into transparent sheets suitable for machining. But that's only part of the challenge. We also had to ensure is the optical performance stable after extrusion? Are there bubbles, internal streaks, or impurities? Any of these could affect clarity and appearance. So, at the material stage, we went through multiple rounds of validation before confirming a workable solution.
Now let's talk about the structure. The part itself isn't large, but it's extremely complex. On the front side, there are dense microtooth features. On the back, concentric optical patterns. These details place very high demands on tooling. We used the microtooth with a radius of just 0.15 millimeters. The smaller the tool, the longer the machining time. For example, just clearing 1/4 of the backside corners takes about 30 minutes, and there are 56 such regions. But the bigger challenge is actually tool access. A 0.15 millimeters tool typically has an effective cutting length of only about 2 millimeters. But the structure depth on the backside reaches nearly 10 millimeters. 3-axis machining simply isn't enough. So we had to use a full 5-axis machining, tilting and rotating the part to guide the tool into position. At the same time, the customer required a flawless surface, no visible tool marks. That means we must use the same tool to complete as much of the machining as possible, minimizing stops and transitions.
Because this is an optical part, it will undergo transparent polishing afterward. So we need to balance everything: geometry, precision, and surface quality. If the surface is too rough, polishing could easily damage those delicate structures. This requires both experience and a careful toolpath strategy. After machining, we move to a critical stage: manual polishing. For transparent parts, this stage often defines the final appearance. Since we already optimized the surface quality during machining, the polishing process becomes more controlled.
For the edges, we use 600 to 800 grit sandpaper to smooth them out, but the microtooth areas are different. They cannot be touched. Any sanding there would destroy the features, so those areas must be polished by highly experienced technicians.
So in the end, a part that normally relies on injection molding was successfully made through CNC machining, 5-axis processing, and precision polishing. Because sometimes there's more than one way to manufacture a part. If you have similar transparent components or parts with complex geometry and high aesthetic demands, feel free to send us your drawings. Let's explore more possibilities together.